All right, this is Geometry A, Unit 6, Lesson 4. What I'm going to attempt to do is see if we can make some sense out of the formal proof of parallel lines. Here's what the theorem says. Theorem. Okay, and it says basically if we have two lines, y equals m1 x plus b, and y equals m2 x plus c. They are parallel if and only if, that means flowing both directions, if and only if the slopes are equal, m1 equals m2, and the y-intercepts are not equal. Okay, the y-intercepts are not equal. So let's start with this. We'll say m1 equals m2 and b does not equal c. Okay, assume that's true. And that the lines are not parallel. And we're going to show that this leads to a contradiction. If they're not parallel, they must intersect. Okay, and if they intersect, that means we should be able to set them equal to each other and find where they intersect. So set y1 equals m1 x plus b equal to y equals m2 x plus c. Okay, so let's do that. m1 x plus b equals m2 x plus c. Now we just said that m1 equals m2, so substitute m1 for m2. Because they're the same, we should be able to substitute. So I get m1 x equals b, right, plus b equals m1 x plus c. By the subtraction property of equality, I can subtract m1 x from both sides, and we end up with b equals c. But this contradicts something. This contradicts that b does not equal c. From before, we assumed that b doesn't equal c. So that proves that the initial assumption must have been false. They must, if m1 equals m2 and b does not equal c, they must not intersect. And that means they are parallel. Okay? So that's kind of the argument that way, right? Now, the argument should flow the other direction as well. What if we assume the lines are parallel? Can we prove that m1 equals m2? Okay, assume the lines are parallel. Y equals m1 x plus b, and y equals m2 x plus c are parallel. If we want to prove that that means that m1 equals m2 and that b doesn't equal c. Okay, so let's again set them equal to each other. m1 x plus b equals m2 x plus c. And let's see if we can find a point of intersection, assuming that m1 does not equal m2. Assume m1 does not equal m2. And we'll show that that leads to a contradiction, and it must be true that they're equal. Okay, so subtract m1 x minus m2 x equals c minus b. So let me show you what the steps I just did here. I subtracted m2x from both sides, and I subtracted b from both sides, keeping the equation balanced. We get m1x minus m2x equals c minus b. Now let's make a little bit of room. Okay, let's factor out x. Factor out x. So we're going to leave m1 minus m2 times x. That's the distributive property in reverse. We just factored out, took out an x that was in both terms. Think of going backwards, distributing the x, you end up with m1x, m2x. Okay, equals c minus b. Okay, and then divide by m1 minus m2. m1 minus m2. Okay, and we end up with x equals c minus b over m1 minus m2. Now we just said that m1 does not equal m2. So if they're not equal, then m1 minus m2 must not be 0. Okay, and this is a real number, which contradicts the fact that they were parallel. We assume that they were parallel, and if we let m1 not equal m2, we end up having a point of intersection. Okay, and this is a real number. So we have a very real x value for the intersect if and only if m1 does not equal m2. If m1 does equal m2, then we have division by 0. We have a undefined slope or undefined x value, and the x value doesn't exist. Okay, let's verify this by finding the y value for both equations. Remember, we have the equations y equals m1 x plus b and y equals m2 x plus c. What I'm going to do is I'm going to substitute the value of x, this value right here, c minus b, m1, m2, m1 minus m2, in for x. Right there and right there. Okay, and I'm going to show that they have the same value, the same expression. So let's do a little substitution here. Y equals m1 times x, c minus b, over m1 minus m2 plus b. Okay, and let's go ahead and work this one. I was going to work them simultaneously, but I'll work this one out separately here. Y equals, distribute, m1c minus m1b. That's just distributing the m1. Okay, I'll demonstrate that with a little diagram. We distributed m to c and m to b, thinking of multiplying m1 over 1. So multiply by the numerator, plus b. Now I need a common denominator, so I'm going to multiply b over 1 by m1 minus m2. m1 minus m2. Multiplying the top and bottom of a fraction doesn't change its value. Okay, so let's go here. m1, m1c minus m1b over m1 minus m2 equals plus m1b minus m2b over m1 minus m2. Now we have a common denominator, so we can add the numerators. Y equals m1c minus m1b plus m1b minus m2b all over m1 minus m2 Get a little bit of canceling out that goes on. M1, negative M1b and plus M1b cancels. And we have, got to be really careful here. There's a lot of steps you can make a mistake. M1c minus M2b over M1 minus M2. Okay, so there's our point. Our point here of intersection is M1 minus M2 over B minus, what was it? No, C minus B, the x value, C minus B over M1 minus M2, comma, that's the x value, and the y value is M1C minus M2B over M1 minus M2. Okay, that's the point of intersection. Let's verify it works out here in this one. Y equals M2 times X. X is C minus B over M1 minus M2 plus C. Distribute. M2C minus M2B over M1 minus M2 plus C. Multiply by M1 minus M2 on top and bottom of the fraction to get a common denominator. Y equals M2C minus M2B over M1 minus M2 plus M1C minus M2C over M1 minus M2. Y equals M2C minus M2B plus M1C minus M2C all over M1 minus M2. You'll notice some canceling, not the same as before. M2C minus M2C cancels. Okay? And so rewriting the order of subtraction here, y equals M1C minus M2B over M1 minus M2. That's the same y value. This y value comes out in both. All right? So the point being that if the slopes aren't equal and the y-intercepts aren't the same, and if the slopes aren't equal and the y-intercepts aren't the same, if the slopes are equal and the y-intercepts aren't the same, then the lines must be parallel and vice versa. Whew. Boy, that's tough.